Now we're ready to fill in the final part. We've talked about the idea of SAT solvers and their need to be able to generate proofs of unsatisfiability, and found that this could be well done with the CDCL solver, except that CDCL solvers are very weak on certain classes of formulas. We've also seen that BDDs can help fill that void. There's some classes, for example, the Parity formulas, that are easily handled with BDDs and very difficult for CDCL. So now the final part is, can we use BDDs in proof generation as well? And the idea is to make use of extended resolution, which, as I've mentioned, has the potential to be much more powerful than ordinary resolution. So we saw the idea was to introduce intermediate variables that encode some shorthand for a Boolean formula over existing input variables and prior extension variables. And we can then use the proof can refer to those extension variables. So now the idea is every time we introduce a BDD, we'll also create an extension variable that encodes the properties of that node as a Boolean function with respect to the other nodes in the BDD. This idea was originated by Armin Bier and two of his postdocs in 2006. Armin Bier, by the way, is the author of Quantification and has been very successful in many aspects of Boolean reasoning. The idea then is, with those extension variables, we can now generate very short proofs for every step of the apply algorithm, justifying the underlying logic of that operation. And in the end, if we end up with the BDD with the leaf value of 0, we'll also have an unsatisfiability proof in extended resolution. So if we think of a node U as having a variable x and children u1 and u0, we'll introduce an extension variable for each of those nodes. And we'll encode as our formula that u, if and only if, the if then else of x, u1, and u0. In other words, if x is true, then u1 and u must be equivalent. And if x is false, then u and u0 must be equivalent. And that, in general, requires 4 defining clauses, as I've shown here. And now when we do the apply algorithm, assume that we're doing the AND operation, and we're doing it over root nodes u and v, both of which depend on variable x. And so, in general, that will create new nodes w1 and w0, and we combine those with to create a variable, a node with variable x that we'll call w. And what we want to do is also generate the steps of a proof that show that the respective extension variables for those nodes, u, v, and w, satisfy u and v implies w, exactly what we'd expect from conjunction. And to do this, we can assume that our recursive calls have also generated proofs of their respective results. And so now we can combine the proofs we generated for these recursive results with the defining clauses for nodes u, v, and w, as is shown here. And you'll see that this is a set of resolution steps where on the left-hand side, we're making use of the case where x is true, and we're using that to be able to, through resolution, to replace u1, v1, and w1 with u, v, and w. And similarly over here, for u0, v0, and w0 under the condition x is false. And that leads to 2 clauses that we can then, through resolution, get our desired result. And this can be done with 2 RUP steps. One to do the case of x true, and the other x is false plus the final combination. So you see that every apply operation will generate at most 4 defining clauses for the new node w, and at most 2 resolution steps to produce the desired result. And so overall, if we apply some large number of apply operations, we'll generate a proof where the number of clauses in the proof will be a small constant factor times the number of apply operations. Another operation we wanted to perform is quantification over a variable, existential quantification. And rather than trying to follow through the detailed steps of that operator, we'll make use of the fact that our quantification operation just takes one BDD U and produces a second BDD W. And so if we think of the respective extension variables, all we want to prove is that U implies W. And we can do this with a separate algorithm that I won't show that traverses the graphs for arguments U and W and generates a proof through recursions similar to what we did for the apply algorithm. And now we can put all this together to create our desired end goal, which is given a set of clauses, produce a proof of unsatisfiability. And the key component of this is something I'll call trusted BDDs, or TBDD. And the idea is this is both a BDD with a root node of T and also a proof of the unit clause T, where now in the second case T is the extension variable that's associated with the BDD root node. And what that states is that any assignment that satisfies the input clauses would cause the function represented by BDDT to evaluate to 1. And I'll use the notation CI double turnstile T, meaning that given that these input clauses hold, we can infer that this extension variable must yield true. In other words, that BDD must evaluate to 1 under the conditions that the clauses are satisfied. And just to sort of look ahead, what we'll want to be able to do is for each input clause, generate a trusted BDD, meaning that not only do we have BDDs with roots T1 and T2 for the two clauses shown here, but we also have proofs showing that the unit clause for extension variables T1 and T2, both of those are unit clauses with respect to the input clauses. And then when we do an AND operation, we'll want to be able to once again show that the conjunction of T1 and T2 yields a BDD that is a trusted BDD, a TBDD. So let's see how that all fits together. As you figure out, we want to generate a BDD variable for each input variable in the formula. And for each clause, we'll want to be able to construct its BDD representation, which is what I called from clause, as well as the proof that this is a trusted BDD with respect to that particular clause. And this proof can be generated fairly simply from the linear structure of those BDDs representing clauses. Those will form our initial set of trusted BDDs. And then as our solver progresses, you remember it will keep performing conjunction operations and quantification operations. And for each conjunction operation, we can assume that the arguments are trusted BDDs, Ti and Tj, and we're going to compute their conjunction, and that conjunction will also produce a proof that Ti and Tj implies Tk, the result. And from that, we can combine that with the fact that Ti and Tj have their own unit clauses, meaning that they're trusted, and we can use that to generate the unit clause for Tk, meaning that it's also a trusted BDD. Similarly, for a quantification, we can assume that the argument Ti is trusted, that the result Tk is generated by this operation, that we've been able to generate a proof that Ti implies Tk, and therefore we can trust Tk. And so this invariant will be maintained as we proceed throughout the SAT solving process. And in the end, when we have a BDD representing leaf 0, which we've derived from that, we can trust that BDD, meaning we have proved that the input clauses imply the empty clause. So it's interesting to look at how different this style of proof is from what we saw with CDCL. CDCL generated proof clauses based on the conflict clauses it encountered, which in a way encoded the necessary conditions for a satisfying solution that slowly get narrower and narrower until there are no solutions. So we kind of took the possible space of solutions and we just narrowed it down until we had nothing left. With a BDD solver, the proof is completely different. It's saying, here's an algorithm, and every step of that algorithm can be trusted to produce something that derived from my original input. And at the very end, my final step will be to produce an empty clause, and that can be trusted by the sequence of steps. So it's more of a step-by-step proof of the execution of an algorithm rather than this idea of taking your input possible solutions and narrowing it down. But still, they're both in the same format. They're both in a DRAT or LRAT format, and they can be tested or checked with the same type of checkers. And those checkers, the LRAT ones, can be formally verified, and so our result can be fully trusted, whether it came from a CDCL solver or from a BDD-based solver. So I've implemented this with a program called TBSat, and it was done by modifying an existing BDD package called Buddy that was generated by a Danish PhD student back in the late 90s. And I augmented the data structures, the algorithms, and the operations of this BDD package to generate and manipulate trusted BDDs and be able to generate proofs, causal proofs, just what you've seen. So if we look at our parity example, you'll see these are the results for the sizes of the proofs that get generated by different programs operating in different modes. So the x-axis is the same before. It's a logarithmic encoding of n. And the y-axis is a logarithmic encoding of the number of steps, either RUP steps or defining clauses in the unsat proof. And you'll see that compared to my runtimes, they're proportional. And so in particular, even though you can see that the proofs being generated by TBSat can be very large, hundreds of millions of clauses, the LRAT checker, it directly generates LRAT format, can handle these. It can scale up to that kind of complexity. You notice in this chart, somehow there's a gap between 10,000 and 100,000, and as you might guess, I'd like to fill in that gap. So the question is, could we do better? Could we find a way to even extend beyond what I achieved with bucket elimination using a BDD-based solver? And the answer, of course, is yes. And it's based on work that I published at TACUS in the spring with the co-authors were Marijn Höhle and also Armin Bier. And the idea of it is to make use of what's known as pseudo-Boolean reasoning, or in this case, it will just be parity reasoning. So directly reasoning about parity constraints as opposed to using traditional causal representation. And so the idea of it is to set up a end-to-end flow that looks like a conventional SAT solver, that we take in a CNF formula and we produce an unsatisfiability proof. But in the middle of it, it operates in a very different mode, meaning that there's a pre-processing program that will detect the parity constraints embedded or encoded in that CNF file and extract them out, and then let a solver be able to reason about those parity constraints and detect that when they are infeasible, there are no possible solutions. That's a sort of well-established concept. Our new contribution to it was to sort of attach a little box to the side which is able to justify the underlying logic of those two steps by using BDDs. So in this case, the real workhorse is the parity solver. It's the one detecting that there's no solution. And we're using BDDs just as an intermediate method of being able to convert the underlying logic of this parity reasoning into a causal proof, a step-by-step proof, actually in LRAT format. And the two things we need to be able to prove are, one, that the parity constraints that I detected in this input file are indeed implied by the input file. And second, as the parity solver operates, it does it by a series of steps. I have to prove that each of those steps is valid by creating a trusted BDD representation of the result. And our solution technique will be based on Gaussian elimination, making use of the fact that the integers modulo 2, or GF2 as it's known, has the properties that are necessary to view it as a system of linear equations and solve it using traditional Gaussian elimination. And so the idea is here I have equations where the coefficients, the variables, and the constants are all 1 and 0, and multiplication is like and addition is like exclusive or. And so the key idea of Gaussian elimination is to perform a systematic way of doing elimination steps, meaning I'll choose some equation, E sub s, and some variable x sub t that I'll call the pivot. And it has the property that x sub t has a coefficient of 1 in this particular equation, E sub s. And then I'll use that equation, E sub s, to eliminate the variable x sub t from all the other equations by just doing addition. And I'll keep doing this for variables until potentially until there's one single equation left. And the possible outcomes of it is, one, I might encounter the case where there's an infeasible equation, one of the form 0 equals 1, and therefore there is no solution. And that's exactly what my unsat case will be. The other possibility, which we won't talk about much here, is if it fails to do that, then it can reliably work backwards through back substitution and find satisfying assignments to the variables. So as I mentioned, we have to do two types of validation, two different types of trusted BDD representations. The first is to get a trusted BDD representation of the parity constraint, the BDD representation of the parity constraint, meaning that that parity constraint is really encoded somehow within the input file. And we can do that by taking the TBD representations of the clauses that encode that constraint, forming their conjunction, which is now a TBDD, and separately forming a trusted, a regular BDD representation of the parity constraint, as we've shown with some examples before, and then use an implication proof to then be able to validate that this BDD representation of the parity constraint can be trusted. And similarly, you saw that the key step of Gaussian elimination is the ability to add two equations or add two parity constraints, form their exclusive or, in other words. And the way they'll do this is we assume we have trusted BDD representations of the two operands, E sub I and E sub j. We'll generate a trusted BDD representation of their conjunction, and we'll also represent an ordinary BDD representation of the sum of these two constraints. And we'll use, again, an implication test to be able to generate a proof then that the BDD representation of this parity constraint, this new one, can be trusted. And we'll maintain that invariant as we manipulate parity constraints. So each of them will be trusted, meaning it will be directly implied by the set of input clauses. And if we can reach the infeasible constraint, then we'll have shown that this set of input clauses is unsatisfiable. So now you see we get to fill out from n up to 100,000. When we use this, Gaussian elimination works extremely well. We can readily handle 100,000 clauses. Here you'll see the time is around a minute. And in fact, we've been able to extend this out for n all the way to 699,051. And that sounds like a rather curious number, but when you go one beyond that, what happens is you overflow the bit representation in Buddy for the BDD variables. And of course, we could just recompile the code to make the field larger, but the main point it shows is that with this algorithm and this technique, we can take what was otherwise an extraordinarily difficult problem where we couldn't get beyond 42 for the solution. And now the problem becomes absolutely trivial. We can basically go as arbitrarily high as we want within a very small amount of time and be able to generate a checkable proof that this formula is unsatisfiable. So you can see that, again, our proofs are something short of 100 million clauses for n equals 100,000, and it gets up a few 100 million clauses for my upper limit. But these are all within the realm of checking possibilities for the LRAT checker. So putting all this together, as I've mentioned, CDCL is a well-proven SAT solution technique. It's worked for wide classes of formulas. It's been very highly enhanced and modified. The power of today's solvers are far more powerful than a decade ago, and those were far more powerful than a decade before. So the progress on these has been better than just the fact that our computers run faster. On the other hand, they have these really glaring weaknesses for some classes of problems that actually arise in practice. These aren't just artificial problems. Parity constraints in particular show up in a lot of real-life contexts. And we've shown that BDDs can sort of help fill in that gap. We showed directly here for parity constraints, and our paper from TACA's 2022 also showed we could handle certain types of cardinality constraints, including the pigeonhole problem. So what I'm promoting is this idea that maybe we could come up with combinations. We could have essentially a collection of engines that are good for different classes of formulas. Causal reasoning, BDD-based reasoning, and parity constraints, other types of constraints. And they can all work together, and they can collaboratively detect that a formula is unsat. And also within the same framework, for example, DRAT or LRAT, they can also generate proofs that the formula is unsatisfiable, so that the overall result is still a checkable proof that the input formula was unsatisfiable. Going beyond this, sort of looking at more the big picture, I think this idea of producing checkable proofs is extremely powerful. I've worked in formal verification for many years, and I've always felt this sense of, we claim we formally verified something, but how sure can we really be? How sure are we that there isn't some bug in our program? In fact, there probably are bugs in our programs. Well, this idea of a checkable proof says that even if our program was buggy, that result is absolutely secure. I don't have to rerun it if I found a bug in the program, because I've generated an independent proof that this formula is unsatisfiable, or that this result I'm asserting holds. And so it would be great to see this not just for the Boolean case or propositional reasoning like I've shown, but for other problems in logic as well. Of course, it becomes a lot more difficult. The frameworks aren't as simple once you get beyond propositional logic. Resolution is still a well-understood idea in other forms of logic, but the proofs get much more complicated. So that's still a very open area, but I'd like to promote this as something that should be done. And I mentioned that if you look at the sort of sociology of how this happened within the SAT community, it's a model for how it can happen elsewhere. That they recognized they needed this type of proof capability. They devised proof formats and proof checkers that could easily be integrated with their existing solution algorithms, but kept those checking formats general enough that new algorithms could come in and also generate it within a compatible framework. So if we could do that for other domains, I think that would be a very powerful result.